Let's start first on the vector group, and then we will go to the battery and battery size and calculation. So let me share my screen to you, team. So generally, what we discussed the auxiliary transformer sizing, and we left with the two parameters. One is the impedance, other one is the vector group. So how to select the impedance as well as the vector group? So impedance will be selected based on the two factors, team. One is generally before in our last sessions, I discussed this one. If you remember, uh, when we are discussing the short circuit current or the downstream, I mean that suppose if I'm having a transformer, and this transformer, this is the downstream, which is a low voltage one, and this is a high voltage. Suppose let's assume this is a transformer which is stepping down the voltage from 220 kV to 33 kV for time being. And let's have this, the rating of the transformer is suppose a 100 MVA transformer. Now and I am having a one more transformer here of similar rating, and I am operating these two transformers in a parallel. So if I want to run the two transformers in a parallel, so I have to check some conditions, that whether the two transformers having the same phase displacement, I mean the so both are having the same impedances or same, and phase displacement or same, some vector group, right? I mean about the vector groups. So why it is much important factor here we have to look into is, so if I'm just considering, if I'm taking the impedance of this transformer, suppose the impedance is 12% of this transformer, and impedance also 12% for this transformer. And suppose let's assume for time being this transformer is not operating, only this transformer is operating. So if this transformer is in the service, then if you find the what is the fault contribution from the 220 kV side, what is the maximum fault? What is the maximum fault from this transformer is, you just calculate the current from this 100 MVA root 3 into 33 kV side, as I am finding out the fault current at 33 kV side. So it's 33 kV, and it's rating under the MVA. No need to add the power factor here. So if you calculate the current here, let's do the calculation. So what's the value I'm getting here? 100 divided by 1.732, 1.732 divided by 33, it's giving me nearly 1750 amps. So my current rating is 1750 amps, which is the rated current at the downstream here. So if I want to calculate the what is the fault current, then the formula you already know what we discussed. This is the base current, is the rated current by per unit impedance. What is the per unit impedance? It's a 12%. So 1750 by 12%. If you do this, 1750 divided by 12 into percentage, if it convert, it's coming to nearly 14.5 kiloamps. 14.5 kiloamps. So it seems that this transformer at maximum it is giving 14.5 kiloamps of fault current at the downstream. And similarly, this transformer, if it is operating at ideal, then this transformer is also feeding 14.5 kiloamps. Right? Now the question was, suppose if these two transformers are running in a parallel, if these two transformers are running in a parallel, then what is a contribution from each one is a 14.5 kA, and this is also 14.5 kA. Now it's leading to nearly 20, nearly 28, 29 kA on this bus generally. But when the both transformers are working on a parallel, if you the impedances will get half dim. So it gives 6%, and this also gives the impedance of 6% offering. So if you just do, and if you're adding it again, it's crossing the limits of 33 kV. Generally, the 33 kV fault current limits are 25 k. We discussed this in our earlier classes. But if you see now, the fault current is more than this. So which is the factor which contributing this mostly is the impedance. So in these cases, what we will do is generally we try to one of the technique is we have to split the buses. We have to split the buses, means we don't want to operate the transformers in parallel. We place some kind of sectionalizer middle of this, so both the transformers are individually operated, or else you have to increase the impedance of the transformer. If you increasing the impedance of the transformer per 12% to the more, so it is in the denominator. Obviously, this 14.5K comes down to 10K or 12K. Impedance is in the percentage. Generally, here, if you look into the transformer vector normal equivalent circuit drawing, so this is the R plus JX, and this is the mutual inductance of the transformer. And if you see the second one, so always we are trying to do this transformation ratio by taking one as a reference one, right? So if you take the impedance 12% in the sense, out of all this transformer or impedance, total impedance, so what much of the impedance is mostly contributing on the physical, so on this load, the rated load, it seems. Actually, these are also playing an important factor, right? But these we are not most concentrating. We are only concentrating on this. So this, they're saying that the impedance is some 12% of the rate, of the maximum one. And this again will change with respect to your tap changings also. Means in a pure, fine. So coming to this, as I said, the impedance, it's generally related to the what is a loss that you can see in this reactance, full load due to the winding resistance or for the leakage reactance. And this is again depends upon the load, means I mean rated voltage. If the voltage is this to 33 kV, what would be the impedance? So it seems it is simple way that the this percentage impedance of a transformer is a voltage drop on full load due to the winding resistance and the leakage reactance, and this is expressed as a percentage of the rated load. So this impedance will change with respect to the tap ratings. So that is the impedance offered by this transformer at base load.